Drivers allows us to automatically update different values in our scenes. So instead of having to manually adjust all values, like the location of objects, we can make them change on their own. This is a super powerful tool that we can use to create really advanced things. Let's see how it works by taking a look at this cube. If we look in the Properties panel, we can see the cube's location along X, Y, and Z. These are all values, and in this case, they are values representing a position in space. If we change the X location value, you can see that the cube moves along X in our scene. But that is also everything that is changed. If we change the Z location value, it only affects this cube's location along Z. All of these values are completely independent and don't affect or are affected by anything else. This is not true anymore when we start using drivers. Let's try adding one. Hover over the location values, right-click, and select Add Drivers. The location values now turn purple. This is how we know the values are now being controlled by drivers. To remove them, just right-click and select Delete Drivers. Now the purple disappears. If we right-click on the Z location value and choose Add Single Driver instead, only that value turns purple, becoming controlled by a driver. If we look at a value without a driver, like the X location above, it can be changed to anything we want. There are no limits. This is because the value is not controlled by anything else. However, if I try to change a value with a driver, like the Z value, nothing happens. The value is changed in the UI, but the cube doesn't move, and whenever I let go, it returns to 0. I can't manually control it anymore. This value is now being controlled by something else. To see what, we need to open our driver window. It is located in the graph editor, Drivers. Here in this list, you can see all the drivers your selected object has. Our object only has one, the Z location. Let's select it and open the Properties panel. It is here we can set up the rules for how the value is controlled, making the driver actually do something. Currently, we are using what is called a scripted expression. This is the default type of driver. If we click on it, you can see that we get a list of other types available. It looks like there are many options, but there are really only two. Either you use the scripted expression or you use the rest. In this part, I will use the scripted expression since it makes it easier to learn how drivers are working. I will go over the other ones in a later part. Right away, we can see that we have an error here. This is because in Blender 2.7, scripted expressions are not running automatically for security reasons, even though they are the default type of driver. It is just because you don't want these to be used in a file from a bad user. That is why if we want them to work, we have to tell Blender, yes, I am trusting this file. If this was an unknown file I had downloaded from the internet, I would not trust it, since I don't know if the one who created it had bad intentions or not. But since this is a new file I just created myself, I can trust it. To tell Blender that we trust it, we have to save the file somewhere first. After it is saved, a Reload Trusted button appears next to the error. Any new changes you have made will disappear when you click Reload, so make sure you have just saved. If I now click Reload Trusted, the error disappears and the driver is now working. Since we are using scripted expression, it is this expression field that decides what value the driver will get. Currently, it says 0.000. That's why we can't change the value to anything else when we try to drag the slider in the Properties panel. The field is in control of the value and the field says it should be 0. If we change the field to 5, you can see the cube is moved 5 steps up and that the Z location in the Properties panel now says 5. We are now affecting the location of the cube by changing the contents of this field. The magic about this is that we can do math in this field and whatever the result is will become the Z location of the cube. For example, if we write 1 plus 2, the cube is moved 3 steps. If we add a times 3, it is moved 7 steps. 1 plus 2 times 3. Now this is pretty static and no matter what numbers I choose to write here, I could have written it directly in the Properties panel instead of using a driver. So let's go to the interesting and useful part, and that is that you can use values from other places in your file. This way we can make different objects affect each other. Beneath this expression field you have what is called variables. We have a big add variable button and also one variable already created by default named var. A variable is where we get the value from something else and use it. Let's try to take a position value from this sphere by adjusting the default variable. First we select the object that holds the value. Let's use sphere. Now that we have selected an object, we can choose what value from the object we want to use. Let's select the C location. Since the sphere is positioned 3 steps above the ground, the variable gets a value of 3. You can see the current value of the variable here below. Now this variable will always hold the same value as the C location of the sphere. So how are we going to use this variable in the driver? By simply writing its name in the expression. In this case, the name is var since that was the default. So remove everything and write just var instead. Since the variable has a value of 3, writing the variable name in the expression field gives the driver a value of 3. Writing the name of a variable in the expression does the same thing as writing a number, except that the value can change. Now the cube is 3 steps above the ground, just like the sphere. And if I move the sphere, the cube moves as well. The C location of the sphere becomes the C location of the cube. This seems very simple, just copying the height of another object. So let's make something that isn't quite as straightforward. If we in the variable change the channel to use x instead, the cube is now 5 steps below the ground. This is because the sphere has a location of -5 along x, so the driver gets that value. The x location of the sphere becomes the C location of the cube. And if I move the sphere side to side, you can see how the cube moves up and down. As you can see, it is very easy to start making things complex. Now, we don't have to just use the straight value from the variable. Since this field allows us to do math, we can change the expression to say var times 2. We are now taking the value of the variable and multiplying it by 2. The sphere is -5 steps along x, so the variable value is -5. -5 times 2 equals -10, and as you can see, the cube is moved 10 steps below ground. We can continue doing more, making the expression as complex as we want. If we add 2, the cube is now 2 steps higher than it was before, at 8 steps below ground. -5 times 2 plus 2 equals -8. We can use multiple variables as well. Let's include a third object, a cone, to test it. Let's add a new variable and name it cone. Change it to transform channel like the other variable and choose the cone object, since that is where we want to get a value from. We want the C location, so select that. The driver now gets a value of 2, the same as the C location of the cone. It is always a good idea to name the variable something that says what it is, like when I named this one cone. This makes the expression clearer. The name of the first variable, var, doesn't really say anything, so let's rename it sphere instead so we know what it is. Now, let's try to change the expression a bit from say +2 to +1. When we press enter, we get an error. This is because there is something wrong with our expression. The problem is that there is nothing called var anymore. We have changed the name of the variable. If we change from var to sphere, as the variable is now called, the error disappears. Here we can see that what we write has to be correct, otherwise Blender won't understand and it won't work. Now, let's try using our second variable as well, the cone. Replace the current expression with sphere plus cone. Both the values are now added and the result is then used for the location of the cube. Let's change back to using the C location of the sphere to make it easier to see what is happening. The C location of the sphere is 3 and the C location of the cone is 2, so the cube is moved 5 steps. Using this powerful expression field, we can create just about any result we want by changing the math inside. But don't fear if math isn't your strong suit. Mostly we will only need simple things, like multiplying, dividing, adding, and subtracting. This concludes the first part. Now you have seen how we can add a driver to a value of our choice and then have that value update automatically when we, for example, move something else. And by changing the expression, we can change what value it gets any way we want. Great. To make this explanation clearer, I want to start by defining two things. First, the driver value is the value the expression creates. You can see it here. Driver value equals 5. We take the sphere plus cone, 2 plus 3, and this is the result. The value with the purple background, on the other hand, is the final value. It is the end result of the driver, the location the cube actually gets. Now you might wonder why I need to make a distinction between the two. So far, they have always been the same. If the result of the expression was 5, the C location of the cube would become 5. However, this is only the default behavior. The driver value is actually not the final value of the driver. There is another step in between, this curve. Let's resize the window and zoom in so we can see it more clearly. First, the expression creates the driver value, which in this case is 5. Then the driver value goes into the curve and out comes the final value, which becomes the C location of the cube. We can follow this white dotted line to see what the curve is doing right now. We start at the x-axis with a value of 5, the driver value, and then we follow the dotted line, hitting the curve, switching direction, and continuing until it reaches the y-axis at a value of 5, the final value. The x-axis is what goes into the curve and the y-axis is what comes out of the curve. A driver value of 5 gives us a final value of 5. No matter what value we put into this curve, we will always get the same value back, since it is completely straight and even by default. The dotted line will always point at the same two numbers on both axes. That is why we could ignore the curve in the previous part. If we don't want to use it, it doesn't change anything. However, the curve is very useful, so of course we should use it. By changing it, we get absolute control over the final value of the driver without having to try to find a way to get the expression to do all the work. Let's try adjusting the curve by grabbing this key and moving it 1 unit up, making the curve twice as steep. Now the C location of the cube becomes 10 instead of 5. Since every point along the curve is now twice as high, or low as it was before, the final value of the driver is now twice as big. The driver value of 5 goes into the curve, becomes a 10, and the cube gets a C location of 10. The curve is now multiplying everything by 2. 5 times 2 equals 10. Instead of just changing the angle, let's also try moving the entire curve. Grab both keys and move them 3 units down. Now every point along the curve is 3 units lower than it was before, giving us a final output of 7 instead of 10. The final value of the driver is now the value of our expression times 2 minus 3. As you might suspect, we could get the same result by adding a times 2 minus 3 to our expression directly instead of using the curve. But I think it is important to understand how moving the entire curve affects the output. Don't worry though, the curve is much more useful than just doing simple math, but I want to start off easy. Now we have tried to move the keys around to change the curve, but we don't actually have to modify the shape of the curve manually. Under the variables we have modifiers we can add that changes it in different ways. Just like modifiers for meshes, these changes your entire curve with the click of a button and they can be removed at any time. Click Add Modifier to see all the different modifiers we have to choose from. Let's test creating the same curve as we have right now, but with a modifier instead. We can do this using the generator modifier. First, undo all changes to the curve and then add a generator modifier. If we now want a curve that gives us a change of times 2 minus 3, like the one we just had, all we have to do is to enter this information into the modifier. Times 2 and minus 3. Now the curve looks the same as it did before. Modifiers holds a lot of different possibilities. They don't just help us do simple math like this. If you have a certain problem, the right type of modifier might just be what you need. Let's remove the modifier. Now, the real interesting part of curves is when they stop being straight. Let's grab the handles and rotate them to give it a bent shape. Remember, the x-axis is the value that goes into the curve, the location of the sphere, and the y-axis is what comes out, which becomes the location of the cube. So, what happens if I move the sphere now? Since the curve is not straight, the cube will move at different speeds. Before the bend, the slope is very flat, so the sphere has to move a lot for the cube to even move a little, making the cube move slowly. After the bend, the slope is very steep, so the sphere has to move very little for the cube to move a lot, making the cube move fast. Let's test moving the sphere to see if we were right. It starts slowly, but quickly gains speed, like we predicted. So far, we have only used the two keys that already exist, but we can easily make the curve as complex as we want. Simply duplicate the keys, place them where we want, and adjust the curve shape by moving the handles. This concludes the second part. So, to summarize, what does the curve really do? It gives you the power to change the final value of the driver regardless of what value the expression creates. So if you want to, we can create a curve where 2 becomes 5, 2.1 becomes 10, and 2.4 becomes minus 465. The driver value and the final value are on different axes, so they are completely independent. No matter what value we get from the expression, we can turn it into something else using the curve. Super powerful. In the previous parts, we only used a driver type called scripted expression. Now when we understand what it does, it is super easy to understand what the other options do. Click on the scripted expression to see what we have. There is averaged value, sum values, minimum value, and maximum value. All of these are basically shortcuts, common things you might want to do. They are limited, but in many situations they are enough, especially since we have the ability to modify the curve. Let's take a look at what each of them do and also compare how we would accomplish the same thing using the scripted expression. Sum values gives you the sum of all your variables. It is the same thing as writing an expression saying variable 1 plus variable 2 for every variable you have added. It is exactly what we have already done here with sphere plus cone, adding all of our variables together. If I switch from this scripted expression to sum values, you can see that the driver value stays at 5. Averaged value gives you the average value of all the variables, which in this case is 2.5. To write the same thing as a scripted expression instead, we would add all the variables, sphere plus cone, and then divide everything by the number of variables, 2. Now we get the same result, 2.5. The maximum and minimum value gives you the value of the variable with either the highest or the lowest value. If we select maximum, we get 3, since it is the highest value any variable has, and if we select minimum value, we get 2, since it is the lowest value any variable has. To do the same thing with the scripted expression, we can use what is called a function. They are something you can write in the expression to get things calculated for you. There are a lot of different math functions included that we can use whenever we want. I have included a link with all the functions available below the video, so you can take a look later and see if you find something useful for your own projects. In this case, we want to use either the max or the min function. To use a function, we write the function name, a parenthesis, the variables we want to use separated by commas, and then an ending parenthesis. Let's try using the max function. Write max, parenthesis, sphere, comma, cone, parenthesis. Now the driver gets a value of 3, and if we change it to min, we get a value of 2. Super easy. The function takes these two variables and gives us the correct value back. As you can see, there is nothing these other options can do that the scripted expression can't. It is the scripted expression that gives you complete freedom and flexibility. But they are easier to use. You don't have to write anything, and you can't get any errors from doing anything wrong. They are less flexible, which is also why there is simply less that can go wrong. They also offer another distinct advantage, and that is that they don't create any security warnings when someone opens your file. They will just work. This might not matter if you work on a project yourself and you are the only one using the files, but if you intend to share them online, consider trying to do everything without scripted expressions. Unfortunately, there are many things that can't be done using the other types, so for absolute control and flexibility, scripted expression is the only option. But for simpler things, they are often enough since you get a lot of power from being able to adjust the curve. This concludes the third part. As you have seen so far, there are often several ways to accomplish the same thing. However, it doesn't matter which method you choose, as long as the driver gets the correct final value. Just do what you feel works best for you. Whenever you see a value in the UI you can change, it is an example of a property. A property holds a value. The location property, for example, holds a value representing a location. Every type there is, like object, mesh, camera, light, etc., has different kind of properties unique to them. Objects has, for example, a location property. That's why the cube, light and lamp all have a location property. They are all objects. But only the lamp has a cast shadow property. That is because it is the only object that holds lamp data. And the camera is the only one with a focal length property since it is the only one that holds camera data. Let's take a look at this cube. Here in the Properties panel, we can access a few of its properties. When we used the C location of the sphere to move the cube in the first part, what we were actually using was the value of the location property. Let's do this again by adding a driver to our cube's C location. If I change the default variable to use the C location of the sphere and set the expression to var, the name of the variable, it works like before. The C location of the sphere becomes the C location of the cube. Now this works great in this case, but let's say I would rather use this X dimension instead. Perhaps I have a few modifiers that changes the object shape and I want to know how wide it is. Well, let's just select the X dimension from the list then. Except it doesn't exist. Here we can only choose location, rotation and scale. Does that mean that we can't use the dimension property? No, it just means that we have to give up our very easy to use list of transform channels and start using the real way of getting values from properties. If we click on this transform channel, you can see that we have 4 options. 3 of these are basically shortcuts, and one of them is the general purpose way to access properties. By using distance, we can select 2 objects and get the distance between them without having to do any math ourselves. Very convenient. It's the same thing with rotational difference. This gives us the difference in rotation without us having to do any math. Transform channel is the one we just used, giving us a list of location, rotation and scale. Finally, we have single property. This is the one that can be used for anything. Select it. Now you can see that we are greeted with an empty field with what looks like a DNA string next to it. This field is asking for the path to a property. When using transform channel instead of single property, we selected C location in a list to get the C location of an object. Let's try to get the same C value but by using single property instead. So, what is the path to the C location value? This can easily be seen thanks to the tooltip that shows up whenever you hover over a value in the UI. Let's select the sphere and hover over the location values. The tooltip pops up. Let's focus on the last line, the one that looks pretty long and intimidating. This line holds all the information we need. The first part that says bpi.data can be ignored. After, it says objects, sphere, location. The first word is the type, object. The second word is its name, sphere, and the third word is the property, location. So what this means is the property named location belongs to sphere, which is an object type. Let's take a look at the camera. Select it, go to the Object Data panel and hover over the focal length value. It says Cameras, Camera, Lens. This means the property named Lens belongs to camera, which is a camera type. It can be a bit confusing what is what when the type and the name is the same. If we change the name of the camera data to say wide shot, you can see the change reflected in the tooltip. Now it says Cameras, Wide Shot, Lens. The property named Lens belongs to wide shot, which is a camera type. Let's try using this focal length value of our camera in our driver to see how it works. Go back to the driver. The tooltip said cameras, wide shot, lens. So let's fill in this information. Click on the little cube icon. Here you have all the different types. The type was camera, so let's select that. Next we will select the name of the camera. Click in this empty field and select the right one. There is only one, wide shot. Now for the final field, the path. Just write what was after the dot. The tooltip said dot lens, so let's write lens. Now the driver value is suddenly 35, the same value as the focal length of the camera. It's that simple. Let's select the camera and change the focal length to 20. Now if I go back to the driver, you can see that it still says 35. This is because the driver hasn't updated properly. You can always force an update by clicking the Update Dependencies button. Now the value of the variable is 20. This also happens whenever you switch current frame, so you don't have to worry about keeping it updated when you're working on an animation, since every time it moves on to the next frame, it is updated automatically. Now let's finish our goal of getting the value of the C location from the sphere. The tooltip of the location property of the sphere said Objects, Sphere, Location. So let's fill in this information. Click on the little camera icon to change the type to Object. Select the name of the object in the list. And finally, let's enter the property we want to use. It said dot location, so let's write location and press enter. The field stays red and it doesn't work. We filled in all the information correctly, so what could be wrong? The problem is that the location property actually holds 3 different values, the location along X, Y, and Z. We have to tell it which one it is we want to use. You do this by writing after the property name a square bracket, the slot number you want to use, and another square bracket. Now the red disappears. In the computer world, the first slot is 0, the second slot is 1, and so on. Since I have written 0, I am getting the value from the first slot, which is X. I want the C value, so I need the third slot, which is accessed by writing 2. Now the driver works just like it did with the transform channel. The C location of the sphere becomes the C location of the cube. For things like the location, I will still be using the easier transform channel option instead of single property. There is no reason to make it harder than it is, but I think it's good to know what the transform channel option is actually doing. Finally, I will show you how you can create your own properties. This is very useful when creating automatic objects, since it allows you to make objects hold values they don't originally do. These can be used as different settings for your objects. And the best part is that the custom properties you create will be available in the UI just like all the other properties, making it easy for you to change the values by either writing or dragging a slider. Let's test adding our own property to this cube so we can see what it looks like. Go to the Object panel and select Custom Properties. Click the Add button. A property called Prop is added. We can drag the slider between 0 and 1 and change its value. This is only the default settings. By clicking the Edit button, we can change the name, the range, and even add a tooltip with instructions in case someone else will be using your object. Let's name it Height and set the range from 0 to 10. In the tooltip, we will write height over ground. Click OK and it is saved. Now it is called height and the range goes between 0 and 10. If you hover over the value, you can see the tooltip so you remember what it does in case the name is not clear enough. We have now added a new property to the cube, which holds a value we can use and change. So how do we use this in our driver? Let's look at our tooltip again to see the path. First you have the type, object, and then the name cube. Then after the dot, it says square bracket, quotation mark, height, quotation mark, square bracket. Whatever is after the dot is the path to the property, so let's write that. Object cube, square bracket, quotation mark, height, quotation mark, square bracket. The variable gets the value 1, the same as our custom property, and when I drag the slider of the property, the cube moves accordingly. We have now added a control in the UI we can use to affect our drivers and ultimately our objects. If you want to, you can copy the path instead of writing it yourself. let's remove the path and try to paste it in instead. Go to the custom property, right-click and click Copy Data Path. Hover over the path field and paste. Now it says the exact same thing as we wrote before. Looking at the tooltip or copy the data path is not really necessary when using custom properties. Let's add another custom property and keep it as default. Now let's try using that value in our driver even though we have never looked at the tooltip. You know what object you added it to, so just select that object. The path to a custom property is always in the form of square bracket, quotation mark, the name of the custom property, quotation mark, square bracket. So to use prop, we can, without looking at the tooltip, just write square bracket, quotation mark, prop, quotation mark, square bracket. And now it is working. Super easy. When we add custom properties in our object panel, they also become available here in the properties panel. This is pretty handy as they are easy to reach. Unfortunately, this properties panel is context sensitive, so the controls might not be available if you switch to a different mode, like pose mode for an armature. That is the reason I often just keep the object data panel open here to the side instead of using the properties panel. That way they are always in reach. If you found drivers interesting, please check out my Mastering Drivers training DVD, where you will learn a lot of cool things you can use the drivers for. It is available now at exploreblender.com.